let's talk about gravitational. So gravitational and spring potential energy. So both the concepts are the same. They just have a little different ways to calculate them. Potential. So potential energy is usually going to be represented by a U, and the subscript is going to determine the type of potential energy. So U of G is just gravitational. You might see U of grav sometimes as well. And gravitational potential energy just calculated by the mass of your object times the gravity times the height it is from whatever you set relative to y equals 0. And I'll show you what I mean by that in an example. And you can also calculate your spring potential energy, S of E. Usually E, it means by elastic potential energy. So like a trampoline would be considered some elastic potential energy producer, or not producer, I guess. You can produce energy. Something that contains elastic potential energy. And you can calculate it like so. So 1/2 K times the x squared. So what is K? Well, K is your spring constant. So K just determines how strong your spring is. So like a steel spring is going to have a larger. So a steel spring is going to have a larger. Steel is going to have K very big. But a toy string made of plastic is going to have a K that's pretty small. And X just is some distance that your spring has traveled from the equilibrium point. So what is an equilibrium point? Well, when a spring is completely still, it just doesn't move. So you can compress it or stretch it. And the distance you compress it or stretch it is x. So let's give you an example of what gravitational potential energy is. Let's say you have a hill. Let's draw this with green, actually. So you have a hill, and you have a ball. A ball on top of this hill is 5 kilos, and the hill is 5 meters high. And currently, this ball is at rest. So the kinetic energy, so the initial kinetic energy is equal to 0 joules. This ball's at rest. But what this ball does have is something called gravitational potential energy. So the term potential energy isn't very accurate towards what it actually is. It's not potential energy. It doesn't turn into energy. It already is there. So you can think of it as a stored energy. So this ball stores energy via the force of gravity. And you can calculate it by using mass times gravity times height. So what is the height in this case? Well, the height is obviously 5 meters because the hill is 5 meters tall. This is set at our y equals 0 point, and our ball's at our y equals 5 meters point. Now, that might seem obvious in this case, but what if the hill, kept going down? Well, relevant to the problem, if you're trying to calculate the kinetic energy of the ball maybe here, you might want to use the y equals 0 at this point because it's a 0. It makes the calculations a lot easier. But if you want to calculate maybe your kinetic energy down here when the ball is down here, well, of course you want to set this point to y equals 0, and you want to not set this point to y equals 0. And when y equals 0 here, of course, your height changes. This maybe will go higher at 10 meters or something. But overall, your y equals 0 point is relative. You can pick it wherever is convenient or relevant to your problem. Like, for example, you wouldn't want to pick the core of the Earth as your y equals 0 point, which technically is your y equals 0 point, because I guess that's the height. I guess that's the total distance this ball can fall into the center until it just doesn't move anymore. But that's not relevant to any of the problems that you're going to solve. So you can set any point to 0. So if you were to calculate your gravitational potential energy in this case, this is mass times the gravity times the height. If you were to calculate, you would get a total energy or gravitational potential energy of 245 joules. So currently, this ball has 245 joules stored up, ready to turn into some other type of energy. And normally, you're going to be turning it into kinetic energy. So this is where the law of conservation of energy comes in. If your ball is, let's say, now it's 3 meters high, it still has some potential energy. It's not y equals 0 yet. When your ball gets to your 0 point in height, that is when the ball becomes or has 0 gravitational potential energy, when y is equal to 0. But what if this ball was 3 meters high? Well, this is where the law of conservation of energy comes in. Your total energy from the very, very beginning was 245 joules, correct? But let's say you want to calculate your gravitational potential energy of the ball here at 3 meters high. Well, you'd want to multiply, again, you want to find the gravitational potential energy of the ball at 3 meters. So the gravitational potential energy of the ball at 3 meters high is 147 joules. Now, where did the other energy go? What happened to the difference between this is what happened to the 245 joules minus 147 joules, right? What happened to that difference in energy? 98 joules in this case. Well, this didn't just disappear. The law of conservation of energy states that the total change in energy must equal 0 joules. So all the energy combined in the system, gravitational, kinetic, and spring, must all stay the same. Spring in conservative forces. With conservative forces that don't dissipate into heat, which I will have a video on that, and I can put that in the description to help you differentiate that. But an example of a non-conservative force is friction. That dissipates into heat. You lose that energy technically out the system, and that energy goes into the surroundings. But in this case, the system is the ball, and this ball's total change in energy must equal 0. Correct? Well, this 98 joules, which is the difference between the two gravitational potential energies here, doesn't just disappear into thin air. This turns into, most likely in most cases when you have gravitational potential energy, this turns into kinetic energy. So you have 98 joules of kinetic energy now. So if you have 98 joules of kinetic energy, you can calculate the speed. You can now calculate the speed of the ball by just using the kinetic energy formula. And once I set up the kinetic energy formula, all you have to do is isolate your speed variable. And with a little bit of algebra, you'll get a speed of 6.26 meters per second. So this ball has a speed of 6.26 meters per second, and all we did was calculate that using potential energy and our law of conservation of energy. So just to add something real quick about springs, it's very similar to how to calculate gravitational potential energy, but if you need anything extra, this is something called Hooke's law. And Hooke's law states that if you multiply the spring constant by the amount you stretch the spring x, you'll get the force. You get the force that you need to exert to get to that x point, how much you need to pull the spring back. And you can actually calculate your spring constant by isolating k here, by dividing x on both sides. You'll get this equation like so, and you can calculate your spring constant by dividing a force by the displacement, or the amount you stretch the string. So this is a somewhat important concept that you need to keep in mind for springs, but let's go on to some problems now. So in this case, you have a bridge, and that bridge is 20 meters. So this bridge is 20 meters above some river. Let's draw the bridge. Oh no, let's draw a very makeshift bridge for visualization, and you have a river flowing down, and this bridge is 20 meters above the water, and there's a person on the bridge. Ooh, that person has slanted legs. That threw a rock at 15 meters per second. So let's use our knowledge on gravitational potential energy and kinetic energy in order to answer this question. Well, we just got to show that the rock, when it hits the water, is going at a speed of 24.8 meters per second. So how do we do that? Well, we know, per the law of conservation of energy, if there's no non-conservative forces, so air resistance is gone, then your change in total energy, total, is equal to 0 joules. So what do we do with that information? Well, that means that our initial energy state is equal to our final energy state. So what are the components? What actually contributes to the initial energy state? Well, what contributes to the initial energy state is, first off, our gravitational potential energy, because we're 20 meters above the water, assuming the water is set at y equals 0. And we also have our kinetic energy. So you're throwing the person through the rock at 15 meters per second. So we have our initial kinetic energy, and we have our initial gravitational potential energy, which is equal to our final kinetic energy plus our final gravitational potential energy. But since the water is treated as y equals 0, your final gravitational potential energy is just equal to 0. No matter what the mass or the gravity is, if the height is equal to 0, then, well, everything is 0 inside of this equation. Therefore, your gravitational potential energy is equal to 0. So let's calculate everything here. Well, in order to calculate initial kinetic energy, you can calculate like so, and we just need to add the initial gravitational potential energy, which is just mg. Let's put the unit, mgh. So h is 20 meters, since we're 20 meters above the water. Now we just need to calculate the final kinetic energy, which is done like so. And as you've noticed, the mass of the rock doesn't matter. You could have done this with kinematics, right? But genuinely, doing with energy is a lot easier from my experience. Trust me, I've literally learned this. Like, when did I learn energy? Like 4 months ago? I learned this 4 months ago, probably, in my physics class. Oh, probably less, actually. Yeah, like 3 months ago. So using energy is a lot easier than using kinematics. But you can actually cancel out the masses on every side, since the mass doesn't matter in this case. So we can actually cancel out the masses, and we can solve for both sides of this equation here. So if you add everything together on this side, you will get a total energy on the left side of the equation of 308.5 joules. And if you calculate everything on the right side of the equation, you'll get a total energy of 307.52 joules. And since these are quite close enough, this makes sense. The law of conservation of energy withheld here, so it worked. It held true, and the total change in energy in this case is equal to 0. Since these are close enough, I guess. I mean, like, if you didn't round anything, if this problem didn't round any of the speeds up here, you probably would have gotten the exact same answer. But you can see why this is helpful or useful compared to kinematics. Let's move on to the next problem. So in this problem, you have a spring this time. So the force of a bow and arrow behaves like a spring force. In aiming the arrow, an archer pulls the bow back 50 centimeters. So let's write down the displacement here real quick. So our change in spring, our spring stretch is 50 centimeters. So that is equal to 0.5 meters as well. And holds in a position of force 150 newtons. If the mass of the arrow is 50 grams, so mass is equal to 0.05 kilos, and the spring is massless, what is the speed of the arrow immediately after it leaves the bow? So let's calculate this. Well, when you pull the arrow back, you're going to have some elastic potential energy. And the moment you release that, all of this turns into kinetic energy. You have no more spring. The arrow isn't even touching the spring anymore. How will it have any elastic potential energy? All of it turns into kinetic energy in perfect conditions. So all we need to do is calculate our spring or elastic potential energy. How do you do that? Well, using Hooke's law, as I showed at the beginning of the video, your force, well, technically Hooke's law is your spring constant times your spring stretched x, or displacement of your spring, is equal to the force. And right now this is perfect because we don't have our spring constant. It's not given in this problem. A lot of times it will be given, but you can use this to solve for your spring force. So we'll divide your force by displacement, and like so, you get your spring constant of 300 Newton meters. And yes, this is the common unit for a spring constant. So if the spring constant's constant, if the spring constant is constant, then your unit will be Newton meters for the spring constant K. This is equal to K here. This is perfect. Now all we need to do is plug everything in. So once you've plugged everything in, this is your formula for your spring or your spring elastic potential energy. So you have 1/2 here. You have your spring constant K, and you also have your amount stretched, which is 50 centimeters. The archer pulled the bow back 50 centimeters. All the other lines are moved. You will get an energy of 37.5 joules. So this is your initial total energy of the system. We're not worrying about gravitational potential energy in this case, since it doesn't mention anything about height. So we'll ignore it for now. So this is your initial total energy. And remember, all this initial total energy, once you release the spring and launch the arrow, turns into kinetic energy. So let's set up our kinetic energy formula here. And once you set up your kinetic energy formula, well, what do you set your kinetic energy equal to? Well, remember, all the spring energy, or the spring stored potential energy, turns into kinetic energy. So you set your kinetic energy of your arrow to be 37.5 joules. And once you do some algebra, your final speed of the arrow is equal to 38.7 meters per second. So for this problem, I already drew it out for you guys. We have a sled at 70 kilos, starting at the left, starting at rest. So initial kinetic energy is 0 joules. That's important to note down. And slides on a 10-degree incline. So I drew that out here. That's 80 meters long. Then travels for 20 meters horizontally, and then before coming back up at an 8-degree incline. For 80 meters, it travels 80 meters. The sled travels 80 meters and along the incline before coming to rest. So the final kinetic energy is equal to also 0 joules. What is the magnitude of the net work done on the sled by friction? So we need to know the magnitude of the work done by friction. So, but here's the thing, we don't have to worry about forces or displacement in this case. We just need to worry about the net work done. And I'll show you why you don't need to worry about that as I do the calculations. So initial kinetic energy and final kinetic energy are all equal to 0. Therefore, the only two types of energy that are actually relevant in this case is the initial gravitational potential energy and the final gravitational potential energy. So we can actually solve these by using MGH, formula above. We have mass. Mass is equal to 70 kilos, and gravity is equal to our gravitational constant. But we don't have the heights. How do you calculate the heights? Well, you have our flat surface here. So what we can do is actually set this. This looks like the best place to set at y equals 0 at the flat surface here. So we need to calculate the heights for both of these hills. Well, you can actually calculate the heights by using some trigonometry. These are technically just triangles, right triangles to be specific. And you can solve for the heights using some basic trigonometric ratios. Your hypotenuses are equal to 80 meters in this case, but you need to find your heights on both sides. So let's say this is initial height, this is final height. So how do you calculate your final height? Well, we can solve for the heights by using some trig, as I've said. So let's use some trig. Let's solve for the initial height first. Let's solve for the initial height. So the sine of 10 is equal to the opposite over the hypotenuse of this right triangle. So the opposite over the hypotenuse is hi, that's the opposite side, and the hypotenuse is 80 meters. So if you were to isolate hi, or initial height, you would get an initial height of 13.89 meters. 13.89 meters. So this side length here is equal to 13.89 meters. Let's solve for the other height, the final height. So again, we're going to use sine. So sine of 8 degrees is equal to the opposite over the hypotenuse. So the opposite side of 8 degrees is the final height over the hypotenuse, 80 again. And if you were to just solve for this, you would get a height of 11.13 meters. So now that we have the two heights, we can calculate your gravitational initial and final gravitational potential energies like so. So I've set up the formula of your mass, gravity, and height here. This is how you calculate gravitational potential energy. So this is for your initial height, and this is for your final height. So as you can tell already, these will not be equal to each other because of friction. So what we can actually do is solve for the difference between these values to get how much work friction did. So let's solve for that. 95.28 joules. Let's round up. So this is approximately the amount of joules, or the energy of your initial gravitational potential energy, and your final gravitational potential energy is equal to 7,635 joules. So they should be equal to each other, but what happened? Well, there was friction along the way. So your change in energy is still, your change in energy in the universe is still 0 joules. But friction released the energy into the surroundings rather than maintaining it in the system. And in this case, the system is the sled. So the difference between these two energies is just 1,893 joules. So the difference between these two energies is the work of friction. And technically, the work of the friction is negative, since your initial gravitational potential energy is higher than your final gravitational potential energy. You technically decreased in work, so your work is technically negative. But this problem asks for the magnitude of the net work done. So this will just be a positive 1893 joules. So if you're still confused about conservative and non-conservative forces, I will have a video link in the description for conservative and non-conservative forces and how to, I guess, differentiate them. So if you have any questions, put it down in the comment section. Again, as always, let's erase all this. As always, mention OpenStax. I got my questions off of there. Online textbook. Link will also be in the description if you're curious.